Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. So within this module, we're trying to understand that how does the operating system manage the CPU by providing this abstraction of a process. And within the second module, we are currently on the fifth topic, that is time sharing. So, as you know, in this topic, we are talking about the concept of time sharing, where the operating system shares the CPU time among the multiple processes that are there in the system. So, this technique basically allows us to run more number of programs on limited number of CPUs. And this concept of time sharing, as we know, is implemented via something called as CPU scheduling. So, in CPU scheduling, the operating system allocates, or we can say schedules, the CPU among the multiple processes in the system, right? And in order to understand CPU scheduling, there are several questions that we need to answer. So currently we are focusing on the how part, that is, how is this CPU scheduling implemented? What is the mechanism behind this, right? So the first part in understanding the mechanism behind CPU scheduling is to understand that how will the user process give control to the operating system, right? Because unless the operating system has the control of the CPU, it cannot perform CPU scheduling. So the first part is transferring control to the operating system. And in the previous video, we have talked about an approach where we are trusting the user process to give up the control of the CPU on their own, right? But we saw that there are several issues with that approach, right? So in this video, we are going to look at the alternative approach, where we are going to take away the control of the CPU forcefully from the user process, right? We would not wait for the user process to give up the control. We will take it forcefully and transfer it to the operating system. So this is going to happen using something known as a timer interrupt. So let's study in this video what is a timer interrupt and how does it work. So let us start the discussion with this slide. This slide basically shows the different questions that we are trying to answer with respect to CPU scheduling, right? That is why, how, when, who, and which. We have already answered this question why, right? Why do we do CPU scheduling? It is because it helps us to implement the concept of time sharing, right? Which enables us to run more number of programs on limited number of CPUs, right? So currently we are focusing on the how part, that is what is the mechanism behind CPU scheduling, how it is actually done, right? So first of all, it should be even possible to do it, right? Do the CPU scheduling on a computer system, right? So that is why understanding the how part, that is how CPU scheduling will happen, is important, right? Then once we have understood how, we can talk about the different remaining other questions. So in order to understand that how is the CPU scheduling done, we had broken the problem into multiple parts in the previous video. So let us recall what we had talked about. So as you can see, this is the CPU, and the CPU time is being shared among multiple processes. Here we have three different processes, and as you can see, the CPU is being shared between these three processes. Right, this is the time sharing that is happening. And how is that happening? So to understand that, let's look at the point where we are switching from one process to another. So if you look at this carefully, there is a process A which is running initially, and then there is a context switch. In context switch, what we do, we pause process, the running process, in this case process A, and then select another process, and they give the control of the CPU to the new process, in this case process B. So there is a process A, right? Then there is a context switch which is followed by the new process, which is process B in this case. And we are interested in this context switch part, right? How will this happen? And so within this context switch, again, we have different parts. So the first thing that needs to happen is that we have to transfer the control to the operating system, right? So currently the user process is running, right? And for the operating system to do any kind of scheduling, for the operating system to select a new process, all of that will only happen when the control of the CPU is with the OS. So currently when process A is running, then as that means that the control of the CPU is with process A, right? Operating system does not have the control of the CPU. So the first part, that is the most important part, is to transfer the control to the operating system. And once the operating system will have the control, then only it can select some other process, right? Select next process, then it will make the switch happen, switch to next process, and then give the control back to the user process. So first of all, we need to figure out this part, and that is what we had started talking about in the previous video also, right? So how can we transfer the control to the operating system? We said that there are two different approaches to this. One is the cooperative approach, about which we talked about in the previous video, and the other is the non-cooperative approach, which we'll talk in this video, right? So let us recall how the cooperative approach works. So in the cooperative approach, we are trusting the user process and assuming that it will behave reasonably and give control to the operating system. So basically, in the cooperative approach, we are waiting for the user process to give up the control of the CPU on their own, right? We are assuming and trusting the user process that they will voluntarily, right, that is on their own, give up the control of the CPU to the OS, right? But we have seen that this is not a good idea, right? Expecting the process to behave is not reasonable, right? The user process, there can be times where the user process would not give up the control of the CPU, and in that, if that happens, then we cannot perform CPU scheduling, right? The user process will keep the control of the CPU with itself, and then the operating system would not be able to run. So in those cases, we will not be able to perform CPU scheduling, right? So we had seen an example of this in the previous video. For example, if a user process has a bug that let's say the user has written an infinite loop, right? It could be a bug or it could be intentional. And as you know, if there is an infinite loop, then the user process would just keep on executing, right? So if you recall that we had talked in the previous video that what are the reasons why the user process would give up the control. The reasons were that it could invoke a system call, right? Or it could like make a mistake, that is there could be an exception and then it would terminate, or there could be some kind of device interrupt. So we were relying on traps, that is system calls, exceptions or interrupts, for the user process to give up the control of the CPU. If the user process is on an infinite loop, right, then it won't be calling system calls, it won't be making any exceptions, and let's just assume that during that duration there is no device interrupt also, right? If none of these happen, then as you can see, the user process would not be giving up the control of the CPU to the operating system, and now we are in trouble. So we said that in the previous video, the only option that is left with us is that we need to reboot the computer, the whole computer system. When we reboot the system, the process will be terminated. Obviously, the whole computer will start fresh. But this is not something that we want to do. This is not a good approach, right? This is not the way we want to use the computer. So the cooperative approach, where we are trusting the user process to give up the control voluntarily, obviously does not work, right? So what is the other approach? The other approach, that is the non-cooperative approach. Here, the operating system would require support from the computer hardware, right? The operating system alone cannot solve this problem. It needs help, and it needs help from the computer hardware. So there will be some kind of hardware support. That is what we'll study in this video, that is timer interrupt. So basically, what is this hardware support? Here, if you see, to solve this problem where basically a user process is like hogging the CPU and not giving up the control, we need some kind of help. So in the previous video, we took the extreme action, that is we rebooted the computer system. Instead of rebooting the system, can we interrupt this user process in some way so that we don't have to reboot the system and we get the control of the CPU in a more graceful manner? So this is an extreme step. We want something which is less extreme. We want the control of the CPU to be forcefully taken away from the user process without going through reboot, right? So that is where we'll have some piece of hardware, and that is timer interrupt, which will help us to take the control of the CPU in a graceful manner. So this is the non-cooperative approach, where we have a hardware device that is called timer interrupt, and it supports the operating system to regain the control of the CPU. So let us see what is this timer interrupt and how does it work. So before we talk about timer interrupts, first let's revisit the concept of interrupts. So what is an interrupt? An interrupt is basically when a hardware device, right, it is raising some kind of notification or a signal to the CPU that signifying that it needs immediate attention from the operating system, right? And when that happens, when a hardware device raises an interrupt, what does the CPU do? So once the CPU detects that there is an interrupt from a device, it immediately pauses the currently running user process and transfers the control to the operating system. So once the operating system comes into the picture, it does whatever is necessary to deal with the interrupt. Whatever action is required, that the operating system performs, and that is, we can say, the operating system has serviced the interrupt. Once the necessary action has been performed by the operating system, then the control is given back to the either to the user process that had been interrupted or to a different user process. So this is how the flow of actions look like when we have a interrupt in the computer system. Let's also talk about why hardware devices raise interrupt and what are some examples of interrupts. So basically, most common sources of interrupts are IO devices. So whenever we start, let's say we start an IO operation, and when that is complete, then the IO device raises an interrupt, notifying that the operation which had been requested is complete. Now the operating system can process the data or the like check for the status of the operation. So let's say there was a user process and it had initiated a read on a hard disk, right? So once the data is available, so when the user process initiates the IO operation, it would block, right? Whenever user processes initiate IO operations, they wait for the IO operation to complete. So once the operation is complete, then the device will notify to the CPU that the operation is complete. Now it is a good time that the operating system should unblock that process and then continue further execution. So in the example where the user process had initiated some kind of read on the hard disk, so once the data has been read in from the hard disk, then the hard disk will notify to the CPU to bring the operating system into the picture. The operating system will read the data from the hard disk and unblock that user process, and then the user process can do whatever it wants with the data. So the point is that the most common sources of interrupts are IO devices. We very often start operations, initiate operations on IO devices, and once they complete, they raise interrupts. Interrupts also come from devices which are not IO devices. For example, if the battery is low, right? Battery is a device. If the battery is low, it will signal to the CPU uh, that the battery is low, and it is a kind of urgent thing that the operating system should notify to the user that it is like the user should plug in the charger. Other examples are when we have inputs from the user to input devices. For example, let's say on the keyboard or on the mouse, when we press some buttons, then that is new input that needs to be processed. So whenever the user is giving new input, then these input devices, let's say the keyboard or the mouse, they will be raising interrupt so that the operating system can come and process that data, right? So these are different examples of interrupts, right? So now having understood, having recalled the concept of interrupts, now let's understand what is timer interrupt. So what is a timer interrupt? Basically, a timer is a device, right? That can be programmed to raise an interrupt every few milliseconds. What does that mean? So we are all aware with the concept of timers. We use timers in our daily life also, right? For example, let's say you're cooking something. You want to boil water, but you want to boil it only for 5 minutes. Let's say you are boiling eggs, right? And you know that the egg will boil in, let's say, 5 minutes. If it is less than 5 minutes, then it would be undercooked. If it is more than 5 minutes, then it will be overcooked, let's say. So you want to boil it exactly for 5 minutes. So you put on a timer, right? And after 5 minutes, your timer, it could be in a phone or it could be a physical device, it alerts you, it kinds of interrupts you, and then you can go and deal with that notification. You will turn off the gas, right? So this is one of the examples in which we use timers in our daily life, right? So how does this timer work in the case of computer? In the same way, the computer starts the timer, and the difference here is that once the timer expires, it interrupts, obviously, like real life timers. The difference here is that it will interrupt at every fixed interval. Let's say inside the computer, the timer has been programmed to interrupt after every second, right? So once we have 1 second, once 1 second expires or passes, we will have a timer interrupt. Then again, after 1 second, we'll have the interrupt, and so on. So after every fixed time interval, the timer will raise an interrupt, right? So this is the idea behind timers. They are just like real life timers. In real life, the timer interrupts only once. In case of a timer which is inside the computer, it will interrupt at every fixed interval. The fixed interval is around few milliseconds, and it is programmed by the operating system or the hardware, right? So you can see once you start the timer, the time is expiring, and once the time finishes, the time period finishes, it raises a alarm or a notification, right? So this is the basic idea behind a timer. So just like real life timer, at each tick, at each clock tick, the value decrements, and at zero, an interrupt is raised. So let's say inside the computer, we are setting the timer for 500 milliseconds. So at each millisecond, the timer will decrement itself. After 500 clock ticks, the value of the counter, so the timer is in the form of a counter, the value of the counter will become zero, and an interrupt will be raised. Let's say the timer has been programmed for 250 milliseconds. right? Then in 250 milliseconds there will be 250 ticks, and at the 250th tick the counter value will become 0, and it will raise an interrupt. And it will not only raise the interrupt just once, after every 250 milliseconds it will raise an interrupt. So this is the basic idea behind a timer. It sounds simple, right? So how is this timer interrupt used, right? So let's come back to the problem that we are trying to solve. We are trying to solve the problem inside CPU scheduling, that we want the control of the CPU to be transferred from the process to the operating system. In the cooperative approach, the user process could hog up the CPU and would not, there could be cases where it would not give up the control of the CPU. So now we are relying on explicit interrupts. So in that case, what were the three cases where the user process would give up the control? Either it could make a system call, or it could make some mistake, that is an exception, or there could be some interrupt, right? If the user process is not making a system call or an exception, we are left with device interrupts. We said that if device interrupts are also not happening, then there is no chance of getting the control from the process to the CPU. In that case, we would have to resort to a reboot. But in the absence of interrupts from other IO devices, what we have done is that we have an explicit device that whose sole purpose is to just raise interrupts, right? So the timer interrupt is that device. Even in the absence of like interrupts from any other IO device, right? If there is no interrupt coming from any IO device, even then we have the timer interrupt, which has been programmed to raise interrupts at every fixed interval, right? So what is the result? The result is that there is a guarantee that there will be an interrupt after in a fixed interval, and we will get back the control of the CPU, right? So as you can see, when it raises an interrupt, it is treated like any other device interrupt, right? Whenever we have a device interrupt, we said that the control will immediately transfer from the current user process to the operating system so that it can service the interrupt, right? So now we have a guaranteed interrupt. That is the benefit of timer interrupt. We can be now sure that the control will eventually transfer from the user process to the operating system after every fixed interval, right? And then the operating system can do whatever it wishes. So what we wanted is that the control be given to the operating system so that it can run the scheduler. So as you can see, whenever we have a timer interrupt, it is treated just like any other device interrupt, right? The CPU immediately halts the currently running user process, gives the control to the operating system, and the operating system can do the CPU scheduling. Basically, it can select some other process and transfer control to that different process. In this way, a switch can happen, right? This is what we want. We want to frequently switch the control of the CPU between different processes. And the problem that we had is that the operating system did not have the control of the CPU, and that we have solved by introducing a explicit interrupt, which is guaranteed to raise an interrupt after every fixed interval. So we are sure now that after every fixed interval, in between also there could be interrupts, right? There could be interrupts from other devices. The user process could make system calls, it could make exceptions, it could cause exceptions, but and in that case also the control will be transferred to the operating system. But even in the absence of all of these, right, even in the absence of system call, exceptions, or any IO device interrupt, we are sure that there would be an interrupt from this timer interrupt, right, every fixed interval, so that we can get the control of the CPU to the operating system and perform CPU scheduling. So now, having understood what is a timer interrupt, let us see the overall flow of how the timer interrupt works, right? So let's start with this. So as you can see, here we have a computer system. This is the CPU, and this is the timer device, right? So the first thing that we need to do is that during boot time, with any kind of device, right, we have to register the interrupt handler, right? So what is an interrupt handler? It is a piece of code that will run when the interrupt occurs to handle that particular interrupt, right? So just like any other interrupt, for timer interrupts also we register the interrupt handler, and then we start the timer, right? So starting the timer is also very important. Now once the timer has started, once it expires, then an interrupt will be raised, right? So you can see the timer has started. Once it completes this interval, then it will raise an interrupt. So let's start a user process and see the behavior of the process in the presence of timer interrupt, right? So as you can see, here the operating system has created a process, right? At some point in time, we are assuming that the operating system has created a process and given the control of the CPU to the user process, right? It has started the execution, and now the control is with the user process, right? So the user process has started executing instructions, and let's just say the timer at this point is has finished 1/4 of the total duration. Let's just assume that the timer is 100 milliseconds in this example. So in this at this time instant, let's say 25 milliseconds have been done. After some time, 50 milliseconds is done. You can see the process has executed some more instructions. Then after another like 25 milliseconds, you can see some more instructions were executed. So now 75 milliseconds are done. And as we reach 100 milliseconds, right? Once the interval of 100 milliseconds is done, right? You can see the timer expires and it raises a timer interrupt, right? And at this moment, the CPU detects that the timer has raised an interrupt, and it what it does is that it immediately, just like any other device interrupt, for timer interrupt also, the CPU will immediately halt the execution of the user process, right, and transfer the control to the operating system. Now the operating system will come into the picture and it will service the interrupt. So for depending on the type of interrupt, the operating system will take action. If it is an interrupt from a IO device, let's say from a hard disk, it will do a different task, right? Let's say it will be reading the data from the disk. But for a timer interrupt, it will do something different. In this case, the interrupt has been raised by a timer. So once the operating system gets the control, here it will perform the scheduling part, right? The timer interrupt has been given so that the control of the CPU is transferred from the user process to the operating system. As such, the timer itself does not need any kind of servicing, right? A timer is not an IO device. It does not need any kind of servicing on its own. It is just there to give the control to the operating system. And once the operating system has the control of the CPU, then it can decide to schedule the CPU, like that is switch the current process and bring in some other process, right? The operating system will run the scheduler, right? So this is how the timer interrupt will be serviced. And let's say we switch to some different process. We can also run the same process again, depends on the scheduler, totally depends on the scheduler. The scheduler can decide which process will run, and the decision can go either way. It could also run the same process, right? We will talk about scheduling decisions, scheduling policies in the next topic, right? But once the scheduler has been run, it could pick either the same process or some other process, right? So this is how you can see now we have a way for transferring the control from the user process to the operating system. So, right, so in this case we can be sure that the user process, once it has started, you can see this does not hog up the CPU. After a certain time interval, there is a guaranteed interrupt from the timer, and once that happens, the control is with the operating system, and then the operating system can decide to switch the process out, right? So this was the basic flow of the timer interrupt. This slide illustrates that the timer interrupt works in intervals, right? So as you can see here, we had a timer interrupt, right, at this point. So you know that at this point the timer expired. Once the timer expires, it is restarted again, right? You can see the timer has been restarted again, right? You can see, and it is going and it is going, and this other process was, let's say, executing, and again after some let's say 100 milliseconds in this example, the timer expires. So this the next process that had been started, the new process that had been started, that will again be interrupted, and the control will be given to the operating system. So the timer raises an interrupt at a fixed interval. So this is kind of a recurring activity, right? After every fixed interval, the timer raises the interrupt, the operating system comes into the picture, performs some kind of scheduling operation, and restarts the timer. That is the important thing. After the timer has raised the interrupt, it is restarted so that it can interrupt at the next interval, at the end of the next interval. So this is a recurring thing that goes on and on, and in the computer system. So there is a guaranteed way for transferring control from the user process to the operating system. This is how the timer interrupt works. So this slide shows the detailed steps that happen during any device interrupt. We have already talked about these steps in an earlier video. My point is to show that like any other device interrupt, the timer interrupt also follows similar steps, because the timer is a device, and whenever it interrupts, whatever is the steps that is taken to deal a generic interrupt, that the same steps are followed for a timer interrupt, right? So as we know that for any kind of interrupt, during boot time, the operating system will register the interrupt handler, right? That has to be run when that particular interrupt is raised. Also, the timer is started in this case. So let's say some user process is running and the timer raises the interrupt. So the first thing that happens is that the trap transfers the control to the operating system, and then we handle the trap, right? In this case, the trap is a timer interrupt. So when we say we have to handle the trap here, the operating system will save the registers of the currently running process. Basically, first of all, you have to halt the current running process because it is not yet done, it is not terminated, right? At a later point in time, it would have to be resumed. So you have to pause the process, and while doing that, you'll have to save all of the registers, because the registers contain the state of the current execution, right? You have to save them so that at a later point in time, you have to restore those registers so that you can start or resume the process that is currently being halted exactly from the same point where you are currently halting it, right? So once the user process is paused, next the operating system determines the cause of the interrupt, and depending on the cause of the interrupt, it will call the appropriate interrupt handler. So in this case, it figures out, okay, this is a timer interrupt, and then it invokes the scheduler, right? So in this part, that is where we are servicing the interrupt. This is where the scheduler will run. It will, based on some scheduling policy, some scheduling algorithm, it will select the next process that has to be assigned the CPU, right? And then we prepare for return. Once we have selected the new process that has to be run, while preparing for return, what do? We restore the registers of the new process, right? When we restore the registers of the new process, we are restoring the context, right? So the new process can start execution from that point, right? We'll talk about this in the next video in great detail. That is a context switch. In a context switch, you have to save the registers, select the new process, and restore the registers. So this saving and restoring of registers is part of context switch, and it is required to switch from one process to another, to pause one process and start another. We'll talk about this in great detail in the next video. So as you can see, during preparing for return, we restore the registers of the new process, and then we return from this trap so that the control is transferred to the user process, right? So the new process starts executing. So all of this happens. So the point here that I want to make is that timer interrupts are handled just like other interrupts. They are a form of trap, and the same set of steps are followed. Some things are, the details vary, but the overall steps, right? The overall steps remain the same, right? So here I have written the command that you can use to find out the number of interrupts that are raised in your computer system if it is a Unix machine in 1 second, right? So if you want to find out the total number of interrupts that are raised in 1 second on a Unix machine, then you can use this command, right? So here we have a kernel parameter called config hertz, and as you can see on the system that I ran this command, the output is 250. So what does this mean? 250 timer interrupts per second, one every 4 milliseconds, right? So within a second there is 1000 milliseconds, right? So in this computer system, by default, the in every second there are 250 timer interrupts that are raised. So one timer interrupt after every 4 milliseconds, right? So in this way, you can find out the number of interrupts that are raised in a second on a Unix machine. So you can see every second 250 times there is a potential for a context switch, right? So in there is a in if every in every timer interrupt the process is switched, then at least 250 processes will get to execute on the CPU. What I mean to say is that 250 process can get to 250 different processes can get to execute on the CPU if we consider that every time there is a timer interrupt, we do a context switch. It can be even more than that because it's not just timer interrupt. There could be system calls or exceptions or interrupts from other IO devices also in between where the operating system could make a context switch. So the point is there are several context switches, frequent switches between processes in a given second. So guys, we have talked about the non-cooperative approach also, right? So the problem that we were trying to solve is that how do we give the control from the user process of the CPU from the user process to the operating system. So in the previous video, we talked about the cooperative approach where we trust the user process to give up the control on their own. And in this video, we talked about the alternative, that is the non-cooperative approach, right? Here, the operating system requires support from the computer hardware, right? So computer hardware here is the timer device, right? So once we have this timer device and once the operating system has started the timer, then it can feel safe that it will eventually get the control back. This was not possible in the cooperative approach. So this is how the timer device, that is a hardware support, solves the problem of getting back the control of the operating system. So once we have the control of the CPU to the operating system. So once we have the control of the CPU, now the operating system can definitely do CPU scheduling. So one part of the problem is solved. So in the next video, we will talk about what the operating system does once it has the control. That is a context switch. We'll talk about how exactly the switch happens once the control is with the operating system, right? So guys, this was it for this video. Thank you very much for watching. I'll see you in the next video. Thank you.